This lecture is Sequence of Function Part 3. We'll cover theorem number 1 and theorem number 2 in this lecture. So the statement of first theorem, it says that if Fn is a sequence of function defined on AB, where Fn is Riemann integrable on AB for all n and Fn converges to F uniformly, then F is Riemann integrable on AB. That is, two parts are given in this theorem. First of all, Fn converges to F uniformly, where each Fn is Riemann integrable. That is, each Fn is Riemann integrable on AB, that is denoted by this way, and Fn converges to F uniformly, that is given. So we'll have to prove that resulting function is also Riemann integrable. That we have to prove in this case. So let us see the proof. Proof is very easy. As Fn converges to F uniformly, so for given epsilon greater than 0, there exists n such that modulus of Fnx minus Fx is less than epsilon for all n greater than equal to n and for all x belongs to AB. This is because of the definition of uniform convergence. Now, in particular, modulus of Fnx minus Fx is less than 1 for all x belongs to AB by taking epsilon is equal to 1 in this case. Now, modulus of Fnx minus modulus of Fx is less than equal to Fnx modulus of Fnx minus Fx. Here also we will take the particular value and it should be capital N, not small n. So this is from this expression, this is so because we know that modulus of A minus modulus of B is less than equal to modulus of A minus B. We are using this inequality over here. We obtained that modulus of Fx is less than equal to Fnx plus Fnx minus Fx, this expression, and this Fnx is coming from here. Here it should be capital N, and that should be less than equal to 1 plus Fnx using this. So for all x belongs to AB. So we have this Fx is, finally we obtained that modulus of Fx is less than equal to 1 plus modulus Fnx. Now since Fn is Riemann integrable, which is given over here that each Fn is Riemann integrable, so Fn is bounded. That means we can find an m such that modulus of Fx, that is less than equal to 1 plus modulus Fnx, and that is less than 1 plus m. That is, we will suppose that because Fnx is bounded, so it should be less than m. And finally we got that Fx, modulus of Fx, is less than a constant 1 plus m. This implies F is bounded on AB. So first thing we have proved, because two things are required if F belongs to Riemann integrable or AB, if you want to prove, and it should be F is bounded. So this we have proved over here. Now let us take for each n belongs to n, note that let En be the set of points in AB where Fn is not continuous. Let us take En be such a set and define E is equal to union of En. Now since each En is of measure 0, why it is measure of En is of measure 0? Because each Fn is Riemann integrable, so each Fn is continuous almost everywhere on E. So the set of points En where it is not continuous is of measure 0. And because of this, E is equal to union of En, so E is also of measure 0. Now let us take x is any point which lies in AB but not in E. Then x is not belongs to En because E is nothing but union of all En. And if x does not belongs to E, it implies that x does not belongs to En for any n. This implies, because x does not belongs to En, this implies Fn is continuous at x. And as we know that we are given that Fn converges to F uniformly and Fn continuous at X. So this implies that F is also continuous at X. So if we take any point X which lies in AB but not in E, then F is continuous at X. This implies that F is continuous almost everywhere on AB. And we have already proved it is bounded. So finally we got that F is Riemann integrable on AB. By this way we have proved that resulting function F is also Riemann integrable in case when Fn converges to F uniformly and each Fn is Riemann integrable. Then finally the resulting function F is also Riemann integrable, that we have proved Riemann integrable on AB. Now let us see the next theorem, that is also very easy. And statement is let Fn is a sequence of function in Rab which converge to uniformly to the function f on AB, then F is Riemann integrable, that we have already proved. And the limit n tends to infinity a to b Fn x dx is equal to a to b fx dx. Note that it means if this happens, then we can interchange the limit and the integration. Limit goes inside and this n tends to infinity, Fnx become fx. That is, these two can be interchanged. So let us see the proof. As Fn converges to F uniformly and Fn is Riemann integrable for each n, so F is Riemann integrable. That we have seen in the last slide. Now as Fn converges to F uniformly, so for epsilon greater than 0, there exists an n such that modulus of Fnx minus Fx is less than epsilon upon b minus a. That is because of the definition we can find such a n for all n greater than equal to capital N and for all x belongs to closed interval AB. From this, we obtain that modulus of a to b Fnx dx minus integration a to b fx dx, that is equal to modulus of integration a to b Fnx minus fx dx, that is less than equal to integration a to b modulus of Fnx minus fx dx, and Fnx modulus of Fnx minus fx, that is less than equal to, because of this, less than equal to epsilon to b minus a. So we'll replace it over here. That will come out and we get b minus a, and